So, so you have today. You have to wash your minds clean um, from what we've talked about, because so far we've talked about the movement of two fluids simultaneously, non-wetting and wetting, that have contrasting behaviors, and how to be able to understand that. And so today we'll assume that that's the first couple of months, and it's sitting where it is. It has some architecture in its distribution, either within the vadose zone or below the groundwater table, and it looks like these kinds of things we have here. And now we're interested in what happens when fluid, liquid or air, I guess, in the vadose zone flows past it, and how much material it can pick up as it goes downstream. And so we'll talk about diffusive and advective transport of dissolved phases. So rather than moving a single fluid as that fluid, we'll look at stuff dissolved in groundwater. So that will be our approach. If you were taking notes last week, in our discussions last week, we didn't have this A. Sean was puzzled by this, and so this was saturation times Darcy velocity. That gives you a velocity with a concentration attached to it. If you multiply cross-sectional area flow, it gives you a mass accumulation rate, which is what you've been using in the stuff that you've done. So that was that. So today, and starting for the next 3 periods, a bit noisy today. So I'm not picking this up. Yeah, fine. So we'll say something about what we've done so far and how it works into what we're doing. We'll talk about transport in the dissolved phase, both by diffusion, Fick's law, and advection. We'll talk a little bit about the properties that define that behavior in terms of mechanical dispersion and hydrodynamic dispersion. Straightforward. So let's kind of put it in context from what we have. And so just to summarize what we've done so far, actually it'll come back to that same expression that we mentioned, and that is that we've talked about transport along maybe a core, or it could be in situ, and we've talked about pressure changes driving flow along core, and we know that we can define the Darcy velocity as equal to something like a relative permeability, which is a function of saturation, multiplied by a real permeability, meters squared, viscosity, am I going to speak up, and a pressure change or a pressure gradient. We know that pressure gradients are a bit tricky to deal with because you have to worry about, we know there's a swimming pool. The swimming pool has a vertical pressure gradient, but it's clearly not flowing. And so we have to look at the bulk weight. But this is good enough for us. If we want to get a volumetric flow rate, we can multiply that Darcy velocity by cross-sectional area. This is cross-sectional area flow. This would be flow at some velocity, or it would also be a volumetric flow rate. And if we wanted to calculate the mass removal rate of a component that's dissolved in water, it would be given by a solubility. So this is saturation of some fluid, I guess we defined fluid alpha, 2 phases, 1 and 2, air and water and DNAPL. This is solubility. It would be units of mass per unit volume. And if you multiply that by a volumetric flow rate, you end up with a mass flux. Or this would be the same as solubility times Darcy velocity times area. And so I think you've used this already, right? To certainly you've looked at velocities, and so you've also looked at advective velocities. And you've looked at the advective velocity is equal to the Darcy velocity. I know it's an alphabet soup. Darcy velocity is what comes from Darcy's law. Advective velocity is the velocity it actually travels with if you were to calculate how far it would go. And you could use this to calculate if velocity is equal to length over time, then the time taken to arrive would equal to the length traveled divided by the advective velocity, or the length traveled would be equal to the product of advective velocity times time. And I suppose if you were to kind of draw that on this, I'm going to draw it back to front, I suppose, that if you put if you looked at the length of this thing here, and you looked at a concentration, which is also would be the solubility, maximum concentration would be the solubility, then you could imagine what you've done so far has been to calculate this. Actually, you have done both, right? You've calculated how far it would go in a given time. So length is equal to advective velocity times the time since it was released. And the concentration would be equal to a solubility. They're all uppercase S's anyway, but that'll make the distinction. So you've done this. How long does it take to get to Longstreet as an analog to how long does it take to get to Las Vegas, basically 120 kilometers away from Vegas for Yucca Mountain. It's in the news again, of course, nuclear power. They're talking about potential repositories. Of course, the US doesn't have one online or planned, which is kind of interesting, after it got quite far in the 1990s before it was stopped in the mid-2008 by Obama, 2008, I guess. I was trying to think which administration. So anyway, so that's what we've done so far. So now we're interested in this behavior. And I guess what we're interested in are a couple of things. One is whether the front is really a sharp front, or whether it would be canted over as it goes downstream. So plug flow or not, I guess, would be one question. And I suppose another question would be whether the front is really set up so that the mid-weight, it's awfully noisy on both sides today, isn't it? The mid-weight of this actually occurs at this point that we said, which is the distance downstream, which is equal to the advective velocity in time. And also, if we drew another curve, I'm getting a bit too involved in this right now, but imagine this going downstream and you plotting concentration, which is this, versus time. And I guess the question would be what this would look like. And I suppose you'd think it would look like this from what you've done before. If Matt gave you any feedback anyway. And this would be the length traveled divided by the advective velocity. So and I suppose the question would be whether this arrival time for the residence time distribution curve would look like the blue curve or the green curve, or it would look like, if I redraw this, or or whether it would look like the black curve and arrive later. So we've assumed some things like plug flow and that concentrations don't change. In reality, there are some circumstances where it will arrive much later because of some processes. And it will also arrive not as plug flow because of processes that go in the subsurface. And we want to define both why that occurs and what the parameters are that cause that. So that's our goal, I think. So we'll talk about that today. Other thing, we skipped this when we talked about fluid flow. But you know, how do we refer to it? What was it? Sean, do I hear you over there? I did. I wasn't speaking up. I saw you as much as I heard you. Good peripheral vision. Yes. Hit me.
Something I wanted to just mention because I missed it. So is the reason we use the Darcy velocity versus the advective velocity to calculate the flow rate? I guess.
One gives you when it arrives. So the bulk motion of the flow is Darcy velocity, and that represents, if you multiply the total area it flows through, which includes the quartz, which it doesn't flow through, then that would give you the volumetric flow rate Q. If you want to know how quickly it travels downstream, it's that velocity divided through by the porosity, because it allows for the fact that it's only flowing through the open part of the pore skeleton, and therefore a given volumetric flow has a velocity which is much faster because it's being squeezed through only 10% of the cross section.
Yeah, I don't know. A different way I thought about it was, well, in the sense that they kind of is the same number either way, because if you think about it, the flow, because it's V times area, well, if you're using the advective velocity, you're going to use the open area, and the open area is
it comes back to be the same.
by porosity versus the actually velocity is divided by porosity, so that cancels the same out.
Yes.
I just wanted to check that.
Yeah.
So I'm
When
okay with that.
all it is one gives you the bulk flow, which is the Darcy velocity. The other one gives you the actual speed at which a particle of water moves. If you want to convert the speed at which a particle of water moves into the volumetric flow rate, you have to multiply by porosity, which I think is what you're saying.
Yeah, but it'd come out the same either way, because if you're going to use the
It is,
velocity,
because if we're anything, we're consistent, and we're thorough, and we're correct. Fine. Okay? Fine. So, do you remember this? This is conservation of mass, right? Density times the velocity gives, velocity times an area gives you a volumetric flow rate. If you multiply volumetric flow rate by density, you get a mass flow rate. And this is the volume in minus volume out is equal to accumulation, equals 0. So the equivalent for that, for this class, is if we wrote this as dfx. Don't write the velocities in, but I'm going to write this as velocity in the x direction with x plus change in velocity in the y direction with y. I'm going to scrub out the vx's in a minute. So that is conservation of volume, actually. It's not if you multiplied both sides by density, you'd have exactly the same relationship that you have here. if, for instance, you replace these with, probably going to regret doing this because we don't need it, but it perhaps means I can go through the other stuff faster. So you remember that we're writing the control volumes for a little differential cube. It's a right-hand coordinate system. So it's x, y, z, it's vx, etc. And we can do those summations. It essentially means volume in minus volume out equals the mass accumulation. So for this, for Darcy's law, let me leave those as that for now. Actually, I'd replace it. I'm going to replace those by a flux, uppercase F, because we'll use that. But it's really a velocity. And you know from Darcy's law that a velocity in the x direction, Darcy's velocity, is permeability over viscosity dp dx, which is really the same as a fluid flux in the x direction. So what we could do is we could substitute these into this in x, y, and z, and if I write it in reduced format just in one direction, we'd end up with k over mu d2p dx squared equals compressibility dp dt. So this is a bit like the groundwater flow equation in Byron's class, or in Rachel Houseco's class. It would be something like d2h dx squared equals specific storage times rate of change of head with time. This is accumulation or depletion, and this is arrival or mass in, mass out. This is written in terms of hydraulic conductivity and head. This is in terms of permeability and pressure, petroleum engineering versus hydrology, but it's basically a statement of conservation of mass. What we're going to do now is we'll use that exact same expression, but now we'll do things like writing Fick's law, that diffusion in the x direction is equal to diffusion coefficient times concentration gradient. And if we substitute that in there, we would end up with something that looks like d change in concentration with location to the second order, because it's already got a term there, which is equal to something like change in concentration with time. So you'll never have to reproduce these equations, but it's useful just to understand where they come from. Basically, we're conserving mass. We're saying that any mass of fluid that goes into this cube either comes out the other side or accumulates, and hence gives us this expression, which allows us to solve numerical models, or using flow nets, for instance, as well, is a simple representation of that. For mass transport, this says that any mass that comes in dissolved within the water that flows into this system either flows out the other side or accumulates. And so this is the balance equation, mass in equals mass out. And what doesn't balance is an accumulation, ACC. And so we'll use that today. And so we'll go through things somewhat using that kind of background. You need to know what the equations look like when they come out and what they kind of mean, and that you can find solutions to them, but it's not a class on PDEs. But that's really where it follows over from 303. That's why we talk about these things in 303. Interestingly enough, when talking 303 about energy balance, so looking at viscous losses in systems, we use Navier-Stokes equations, and we use the momentum balance equation. In potential flow, we don't balance for momentum. We just assume that the drag due to permeability is what retards it, resists its flow. Okay? So, here we go. We can think about two features, and this is actually a useful thing to do. What are you looking around? Are you confused?
No, David just looks sad without Ben.
Ben? Ben hasn't been here for a long time.
Yeah. No, he's been.
No, he hasn't.
Yeah.
I know all your names. It is. I think I know it is. Okay? Anushka. You okay though after Sunday? Get your homework in? Elizabeth. Ava.
Yeah.
Luke. Oh, you're the name at the bottom of the page, aren't you? Last name David.
No.
Okay. It's just no, it's not going to help. William. Yeah.
Yeah, there you
Reka. David Zo. Sean. Julia. Hattie. Yeah, one was a Catherine who corrected me. Katie. Oh, I got you switched. A Maddie and a Hattie. No?
Maddie's there.
Oh, Maddie's there. Where is she?
In the bathroom.
Nicole. There you go. So, I digress. Sorry Ben's not here. So, we're talking about two processes as we go downstream. So, advection and diffusion. So you probably, you've seen Fick's law many times. But the most important thing to realize is that when we talk about these, the easiest analog is to think of a glass of water in which you put a blob of ink. And if you look at the concentration across that blob of ink, it's initially a step function, skyscraper. And because nature abhors gradients, it gets rid of them. And so Fick's law says that it flattens out. The gradient, instead of being infinite, that it is here, if you cant it over its side, it flattens out. And so that's diffusion. In a beaker, it happens statically. But if you look at behavior as you are upstream in a porous medium and then downstream in a porous medium, if you look at putting a drop of ink in the porous medium and looking at its concentration as you go across it, it'll look like this. But as you go downstream, it'll be flattened out just in the same way as if you allowed it to diffuse in a beaker, it would spread out. The peak would reduce in concentration and the edges would expand in radius. And so this is an important concept because these are the two processes that act at the same time in a porous medium. You get the blob being carried physically downstream by advection, which means that it goes a particular length in a given time, which is described by the advective velocity. So you could think of this as being a beaker here at point A and then at point B later on. And as it does that, it spreads out and diffuses. So advection carries the material downstream, but at the same time it also diffuses. But the important thing is that diffusion occurs by two mechanisms. It occurs because it diffuses in the same way that if I'm wearing bad aftershave here, which I don't, you can smell it where you're sitting and progressively further and further away, right? No motion of air in here. But if I moved in the room, you'd smell it faster, right? But this, in a porous medium, this dispersion occurs because the fluid is mixing and traveling between the pore space, and therefore making the diffusion occur that looks like diffusion, because this was what it would look like if it was diffusing, but the mechanism that's causing it is actually mechanical dispersion. Different process. Fascinating? You could barely stop the yawn, couldn't you?
I stopped.
Yeah, I know you did. Well done. So, all right, if I'm boring you, I'll go faster. We'll start moving fast now. So we've seen this. Fick's law defines a flux of dissolved components as it diffuses according to the diffusion coefficient, units of length squared over time. Length squared over time. A mass flux is a mass per volume divided by time. And this is a gradient. Minus sign is because it has direction in the opposite direction of the positive gradient. It flows downstream, if you like. And so if you take this and put it into our continuity equation, which we just talked about a little bit, accumulation, mass in equals mass out, and you substitute this, you end up with an equation like this. And if you take that equation and write it just in one dimension, which we kind of did here, you end up with something that looks like this. So that allows us to accommodate the diffusion coefficient. This is only one-dimensional, so this would be along a core, just like we drew here. So it would be along the length of this core, if it's in one dimension. Or if you can imagine it as being from a point source like me towards you in all radial directions, that's kind of a one dimension. It's the same profile it would get in all azimuths. And that allows us to define diffusion. So this is the diffusion equation, which we won't really use on its own, but it's useful to define it. It's a mathematical, well-known mathematical expression which is called that. If we look at this diffusion, this is the diffusion of my aftershave in an open room which only has air in it, and air is the only carrier. And if the air is stagnant, it's just moving by diffusion. If you fill this room up with sand, so it's an aquifer, then to get that to diffuse towards you, it has to go through the pore throats, and those pore throats only fill up part of the porous medium, just like for advective velocities. And so you could imagine that as this Gaussian distribution, the grading curve, the bell curve, diffuses outwards, it can't go directly to you, but it has to go through some tortuous path because it's threading itself through the porous medium. And so the distribution would have to weave along this pathway that we talked about here, kind of this, between the grains. And so you could imagine this kind of crenulated Gaussian curve that represents the spreading of this as it goes. And so the net effect of that is that the diffusion coefficient, which would be the free diffusion in air of an odor as it gets to you, has to be multiplied by something that represents the tortuosity of its flow path. So that the effective diffusion coefficient in a porous medium, D star, which is what we will use, is going to be this multiplied by something that represents tortuosity. And I suppose you'd think intuitively that this diffusion coefficient would be less effective at diffusing stuff than it would be in plain air, and so this would be a number less than 1. And so indeed, if you figure out what this magnitude would be, it would be some number significantly less than 1, right? 1 over 100. And we could get that if we wanted to. And you'd imagine that it would be related to the tortuosity of that flow length. And tortuosity just means how long the flow length is relative to as the crow flies. Right? You have to go this direct length relative directly from A to B. And so what we could do is we could substitute this term here by multiplying by omega, and then this would become what we've called d star if we wanted to represent a porous medium. And that's all we really have to do. And so if that's the case, then this is our new expression for diffusion in a porous medium. Again, it is being driven by Fick's law. That's all we've done, which is the same as dt times omega. And so that would allow us to deal with behavior in an aquifer. And so if we want to solve that problem, then we can solve the PDE. We won't solve it, but we'll talk about the solution. The boundary condition that would be apply would be that we turn on the concentration from 0 concentration to some concentration. This is time. So I would either not be here, and then all of a sudden I'm here, and have some odor attached to me, and that pervades for all the time class is in. And the solution to this PDE with that boundary condition is this. This is known as the complementary error function. The error function is ERF, C is the complementary, and I think it just means 1 minus. It does mean 1 minus the error function. So ERFC of some coefficient is equal to 1 minus ERF of x. Doesn't matter what the expression is. But the solution to this, if we apply this in time, right? Before this time, nothing. After this time, something. Looks like this. And so if you hold the concentration to be a relative concentration of 1, so 10 milligrams per 1 milligram per cubic meter would be the value, and if you hold it there, the distribution in x turns out to be this after some time. So if you allow the time to increase, the value of this coefficient will change, and therefore the complementary error function will change, and this would merely at earlier times it would look like this and this and this. I'll remove those. So those would be at times 1, 2, 3, and 4. And this expression actually is the cumulative distribution function. So you maybe, I don't know whether you give much thought to it, are all your classes graded on a curve? I guess you just had your stats class as well. Does Randy define his class as geostatistics or as stat? Yeah, but do you do spatial statistics? Do you things like kriging? Have you talked about kriging? K-R-I-G?
It just generally turns into like a general stat class, isn't it?
Fine. It's not spatial. Yeah, fine. Right. So it's a general stat class. So this is the grade distribution, right? This would be a B, this is an A, etc. If you use those things, I don't. So this would be the frequency. This would be the value. So this would be 100%. This would be 80%. This would be 60%, I guess, if you're thinking about grades. This could also be concentrations versus location. So the cumulative distribution function is merely if you started here and you went in this direction and you summed up all the areas to this point here, that would give you this number. If you then go to this point here and you sum up everything to this point, that would give you this drop here, this length. And so by the time you get to this, by definition, this is the mean. And this is the standard deviation, which is either side of the mean. This would be SD. One standard deviation, sometimes you call it sigma, often. So this would be the magnitude of the values, one standard deviation either side of the mean. So you know the difference. You know the difference between a cumulative probability distribution and a probability distribution function? Yes? Averting eyes, looking at tables. Many of you, not all. No? I give up. All right, so that is what the distribution looks like. So in other words, if you look at how a plume would spread, it would spread laterally over time. If you imagine holding this value to be 1 by supplying a constant supply at this point, then it would get flatter and flatter as it goes out, but it would never lose this peak. If you put, for instance, as we talked about, a drop of ink in a aquifer or in a beaker, this is a finite volume that you're putting in. This is the concentration over it. This is the radius in each direction. After some time, this would look like this, right? The peak's gone down because if you think about the mass of this thing would be the area under this curve times its density. As it spreads out, the mass has to remain the same. So the area under this curve has to be the same as the skyscraper. And so to do that, if it's spreading laterally, then the concentration at the peak magnitude has to come down. And so you know, what would it look like at time infinity? Since nature abhors gradients. Or is that too esoteric a question? At time infinity, it's going to be flat, right? Go out to the edge of the beaker. The concentrations everywhere in the beaker will be light blue if it's blue ink. Initially it was a spike in the middle, which was a big color, and white or clear around it. Once it's all become the same concentration, it's a lower concentration, but it's a uniform concentration to the edges of the beaker. And you know that. And so that's what it is. Yes?
I'm just curious. So I noticed on that plot you have there, you have C over C0 and it holds at 1 at X position 0. Are we assuming that then later you draw the concentration comes down? So are we assuming we're holding it?
In this case I am, yes.
Okay. But is that what the differential equation is assuming? Or
Differential equation doesn't assume it, it only assumes boundary conditions. This makes no assumption about that. It assumes that within the medium it varies according to a second order PDE. And so it makes no assumption about the boundary conditions. The boundary conditions are established in this as a function of time and in this as a function of space, that it's held at this magnitude at this location for all time.
yes, the boundary conditions, so we are assuming that we're holding it at that
Yes,
point.
that's a boundary condition.
Okay. 'Cause that's different than having the concentration drop over time.
That's a different boundary condition.
That's just checking.
Yeah.
Okay.
You are correct. You'll be happy to know. So, where now? All right. So, we made the case that we have these two processes. Diffusion, we've said something about in a porous medium, outside a porous medium, within a porous medium, and with boundary conditions. And now, how does it get carried downstream? So the second mechanism is to look at advection. And so it's no different. We know that advection means that we carry something downstream with us. So if you use the beaker analog, it's me taking a beaker, and if I wasn't so lazy, I'd walk across the front of the room with it, and that's physically what advection is. I'm the motivation by which the beaker full of water is being moved from one location to another, and it's carrying that solute in it. In reality, that motion is applied by the bulk motion of the water, driven by Darcy's law. And so now we can think of that flux that's carried by advection as being the advective velocity, this up this A here is advective, the porosity. So actually the advective velocity times the porosity is the Darcy velocity by definition, and the concentration is the mass per unit volume. And so actually, if we multiplied both sides by cross-sectional areas of flow, again, probably more information than you need, then this term here, all in red, would be a volumetric flow rate. And a volumetric flow rate times what we call the solubility, but which we'll now call the concentration, is equal to a mass flow rate. And so the kilograms per day that are carried downstream, mass flow rate, are equal to the volumetric flow rate, meters cubed per day, multiplied by mass per unit volume. This has a volume in it. This is divided by volume, so it becomes a mass per unit time. So the bottom line is that now we can use the same continuity equation that we used before. Ooh, that's pretty fancy. Draws its own arrows if you do that. Is that right? Ooh, that's cool. Don't like it. And so if you substitute that in here and you do the same messing around, you end up with an advection equation. Which says how quickly stuff is carried downstream if it's only moved with the bulk motion of the velocity of the water. And the velocity is going in the x direction, y direction, and z direction at these advective velocities. This again is mass rate in minus mass rate out equals accumulation. It's just the same as before. And there's no diffusion going on here. So if it starts off at a little bead of a bubble of ink, it stays at that shape as it gets carried downstream. And so we've maybe made the case that there are two forms of transport. They look a bit similar. Here's one for diffusion only. Here's one for advection only. And if we put them together, and I'll just write them out here in shorthand, should be a partial, I suppose. Net accumulation is equal to there should be partials, sorry. Transverse dispersion so in these, I guess I'm going to run out of space. This is dispersion. Could call it diffusion, but it's better to call it dispersion. And this term here is advection. And this is accumulation. In a point. And if we solve this equation for boundary conditions which we define, then it starts looking like the things that you can imagine already. Let's not worry about the equations. This is longitudinal dispersion, and so let's assume if it's 1D, One-dimensional would be just flow along a pipe, along a core, if you like. So if it's 1D, then we lose this term, goes to 0, and we're left with the others. And so this is our idea of the boundary conditions. So we have a core, it's like here. If we look, how do I get it to draw the end of a core that's not round? Oh, fantastic. So at this end of the core, we put this boundary condition. So in other words, initially there's no concentration acting on this face, and at some time t0, we turn it on. And we hold it equal to a relative concentration on 1. If we then look at the core, if we could imagine seeing through it, the plume as it goes through the core, after some amount of time, if it's plug flow, it would look like this with the red line. Concentration would be 1 upstream of the front, it would be 0 downstream of the front, and it would still be waiting to arrive. If we wanted to draw a further figure here, a bit like we drew here. Where did I draw it? Ah, here. If we wanted to draw something, I guess that's the boundary condition. I guess we haven't talked about it. If we wanted to do the residence time distribution, which is a concentration versus time, then what would that look like? That's a rhetorical question. I know you're not going to answer it. I won't even look up. Right? What's this time? Length over velocity, is that right? So this would be the length traveled. Right? We did draw somewhere a residence time distribution. I don't know where it was now. So the length that's traveled in a given time will be velocity, advective velocity times time. If it's plug flow, it'll be absolutely sharp, and it will only be concentrations upstream of that, 0 concentration downstream. If it works its way to the end of the core, and the end of the core was some length which we'll call L star, perhaps. Then this would be L star, right? It'll get to the end of the core and it's traveling at some advective velocity. It'll take this long to get there. So the red behavior is for d equals 0. So there's no diffusion. So in other words, if you imagine, if you imagine in your beaker that you put the ink in and it initially has a profile that looks like this in terms of its concentration, then if you come back in 10 minutes and look at it again, it'll look like this again. No diffusion occurring. If diffusion occurs, bless you, that was a silent sneeze. So if this is not equal 0, then these green curves would be from the longitudinal dispersion increasing from 0. So this would be increasing in this direction. This would be 0, the red curve, slightly larger, even larger, even larger. And actually we'll find out that if it's even larger, it will look like this, and it won't go through this point at all. And so that's kind of a description of what this advection diffusion curve means. If we want to get fancy about it and do something else, and so I suppose we could look at it like this. Oops, didn't. I know I'm starting writing over everything. So I imagine we could look at this behavior in perspective, like this. And so if this is concentration on the top and this is length, then this could look like this, right? If I draw this figure out in a perspective as it gets carried along here with the flow of this material. So we could also think of it in terms of a geometry that's more useful to us. I always box myself into doing too much in too small a space, but imagine this is an aquifer now that we have. And instead of putting this concentration upstream here, I'd put this concentration only over a portion here. And so this clearly, if you took a whole bunch of cores next to each other with the same boundary condition on it, it would look same as this stair step, just repeated over and over again. But if you look in plan view as what this would look like, I guess if you drew the contours of concentration as they traveled downstream, they'd look like this, right? This would be a low concentration. This would be the highest concentration here. And it would be a plume that kind of projects, just like smelling someone's aftershave. It travels kind of in all directions. In this case, it's biased that it travels downstream because the bulk motion of the water is carrying it downstream in this direction. And so we can look at both one-dimensional problems and two- or three-dimensional problems. They follow the same equations. I guess I was doing this to note that if it's flow in a single direction and it's constrained within a core, by definition, if you look at the concentration in the y direction, so if you look at dc dy, what is that equal to if you go across the core? So you've started off the red stuff here and here and here and here and here, and they're all going down at the same rate. And so you'd have a whole bunch of stair steps that are parallel to each other. So the concentration change as you go in the y direction has to be equal to 0, right? They have to be mirror images of each other as you go across slices on this. So if the concentration is 0, concentration gradient is 0, then certainly the change in the change in concentration gradient is also 0. The second order derivative is also 0. So that's why this term goes to 0, and we're left just with an advective term, a diffusive term and an advective term. If you have a two-dimensional problem where this y direction, all of a sudden, this is no longer the case, as it's here, right? If you go from the red to outside the red, the concentration gradient changes, so it's not 0. This term has to exist, and therefore the behavior you get is slightly different. Same kind of in principle as this, but different. The other alternative is if instead of holding this concentration constant at the upstream, as we had the discussion about before, you put a given mass in and hold that mass and don't put any more in. So you have a spill into the subsurface, it goes in and it sits there, no more supply occurs. Then the behavior would be that if it's carried downstream, this again would move downstream. It would move down at the rate given by, it would travel a length given by the advective velocity and time. So this skyscraper would translate to this location downstream. If the dispersion was 0, it would be the red curve, be plug flow again. If dispersion was greater than 0, then, or diffusion would be increasing in this direction, right? Just as it did here. It's spreading out more. And I suppose if we wanted to look at the residence time distribution curve, don't tell me, just think in your own mind, don't spoil the surprise. What would that look like? Do you want to tell me? Hey, I'm laughing with you, not at you. So what would it look like if there's no dispersion? This is time. Would it look like this? Yes? Or am I pulling your leg? I think so. Brave. Good. All right, good. Yeah. So bubble has gone past you. It arrives at you. Concentration goes up. And it departs. Right? Has to be. If it was dispersing, what would it look like? I know I'm going to have to wait too long for you to tell me. This would be increasing dispersion. Right? The more it spreads out. So two consequences. Run as it spreads out. By definition, we said the area under these curves all have to be the same, roughly. So by definition, the concentration as it arrives downstream has to be much lower. But the other interesting thing is that this means that it arrives earlier than it should do if it was just plug flow. So that's kind of curious. So if you're banking on it only arriving when it comes equal to this equation here, your SOL, because it's going to arrive earlier. It's going to arrive because it's spreading out ahead of the front. So that's kind of a curiosity. So that's about as well as I can do to try and describe the equations that describe advection diffusion. So this is the equation that we'll use. It's called the advection dispersion equation, not surprisingly. This one's written in 2D. This represents the longitudinal dispersion. This represents the transverse dispersion. So this is longitudinal dispersion. This is transverse dispersion in terms of what it is. This is the advection, bulk motion that's carrying it downstream. And then this is the accumulation at any little grid point that we'd have in here. And so we don't need to know this expression. We just need to know kind of what it means in terms of these figures. And we will want to know what solutions look like if we use those solutions to this equation. So it's all very logical. I think it's all logical. Coming back to this, we made the point that these two mechanisms for transport. We made the point that because this downstream bell curve represents a spreading of the concentration, it actually looks like diffusion, but it's actually caused by mechanical dispersion. And so we should try and understand exactly what mechanical dispersion means. And the reason is we use the fact that it looks like diffusion to try and explain it in terms of an equivalent diffusion behavior, but the mechanism by which it occurs is just by mechanical mixing. And so how do we represent that behavior? So this is the idea. It looks like diffusion, but really it's mechanical dispersion. It occurs because of three reasons, three main reasons. One, if you think about large grains and small grains, then if you look at the tortuous flow path that a particle of dye would take as it gets carried through the system, it will go through paths at different velocities given by the pore throats. Little pore throats will have small velocities, big pore throats will have large velocities, large permeabilities, and so there'll be a different velocity as it goes through on different paths. So it will get stretched out. That's also true in a heterogeneous medium for long and short paths. I guess these are kind of the same. This is a pore size effect. This is a path length, which you could imagine being due to pore sizes. And this is a separate effect, so-called after Geoffrey Taylor, the inventor of this effect. And that is that you know if you get flow in a pipe, that the flow velocity at the walls of the pipe are zero and are maximum in the middle. You know that we can represent flow in porous medium as through a pore throat, which is like a pipe. And so if you imagine dye going through the pore throat at the wall versus the middle of it, this one will move very slowly downstream, this one will move very quickly downstream, so it's spread out. And so as a result of all three of these mechanisms, if you look at the distribution of concentrations downstream, it would look like this. It would spread around a front given by this, and it would spread out laterally. So this would be due to longitudinal dispersion. This would be due to transverse dispersion. Did I call it that before? I think transverse longitudinal. So this by definition would be what we've called the x direction, and this is the y direction. And so what we can do is we can use some way of representing it. And the way that we'd represent it is not a question. I knew. Is that we can take the advective velocity, and if we multiply it by some coefficient, we get this term that we want to use in our PD, longitudinal dispersion, transverse mechanical dispersion. So we'd get these terms that we use here. Not with a star attached to them, but with something else. And so if we want to look overall at the behaviors that we'd want to apply to this system, then finally the values that we'd apply would be this. So this is two components. So this is due to chemical diffusion, and this is due to mechanical dispersion. And so if you want to get the hydrodynamic dispersion, which governs our behavior, which is that concentration traveling downstream is equal to dl d2c dx squared plus d transverse d2c dy squared minus v advective in the x direction dc dx. The velocity in the x direction is the only velocity, so we're looking at an xy coordinate system which would look like this. This would be our little plume that we'd have, that we already drew, that goes downstream looking like this. Then by definition, the velocity driving that flow would be an advective velocity, where the velocity in the y direction is zero, right? Because we're just taking the principal velocity. That's the velocity that arranges the spreading. So it's not related to anything else other than the velocity is going. And so this would describe the spreading that occurs around that. And describes the longitudinal spreading. This coefficient we haven't said anything about, but let's say that we can determine it. This is the advective velocity, and this is the diffusion. And so the important thing about this is that if the velocity is 0, stagnant water, then this term goes to 0, and the longitudinal dispersion is just equal to the effective diffusion coefficient. And the converse is that the advective velocity is a big number, then the longitudinal velocity is dominated completely by the advective component, mechanical dispersion. Ooh, that's cool. Alpha L times the advective velocity in the x direction. And the component, which is diffusion, is 0. It's not 0, but it's tiny in comparison to these other parts, right? And so the reason that we know that is that you could imagine doing a thought experiment. So imagine taking a core where you flow stuff downstream at some advective velocity along the core, and you get the concentration that comes out at the bottom. You use that to calculate the longitudinal dispersion. Imagine you can do that. So we want to calculate exactly what this term is as it comes out without knowing anything about the system in either of these cases. So what we could do is we start off at a very slow velocity and we slowly increase it and measure this dispersion magnitude at each of those velocities. So we start off at, we plot it, bless you, as small velocity. You measure the value of the longitudinal dispersion and you divide it by the diffusion coefficient. This value that we're dividing it through is what we've called d star. And so at this velocity, by definition, the dispersive velocity is equal just chemical diffusion. So you'd expect the ratio of those to equal 1, which it does indeed. So you have one data point. You increase the velocity tenfold, you measure the dispersion, longitudinal dispersion, you get a number which is roughly the same, which is this. You increase it another tenfold, you get roughly the same number. You increase it tenfold again. This dl starts to increase, tenfold again, increases, and tenfold. All that you've done is take the value of dispersion that you measure and you normalize it by the chemical diffusion coefficient. So it's a ratio of numbers that has no units. It's dimensionless. It's 1. And you plot the value of this velocity. You also non-dimensionalize it. You dimensionalize it by, doesn't matter what d is, you divide it through by the diffusion coefficient. And you see exactly this behavior. So when the velocities are essentially very small, then you're on this limb and it's constant. But when the velocities start to get larger, then this dispersion coefficient grows proportional to the velocity as it increases. So I guess on a log-log plot, you'd expect this gradient to be 1-to-1. And that's indeed what you get. So in other words, if you didn't know anything about what you thought this spreading of the dye would look like, you could do some experiments where you'd measure how spread out that dye was when it arrived at the end. And I guess you could do it not I guess, you could do it through the shape of this residence time distribution, because it would change as a matter of the diffusion coefficient. And so if you know what the value of dispersion changes as you push it through at different velocities, you could guess exactly this equation. It's 1-to-1 when the velocities are high, and it's only a function of diffusion coefficient when the velocities are low. And this one is one for the longitudinal values. This is one for the transverse values, but it has exactly the same behavior. At low velocities, it's constant, it doesn't change. And at high velocities, larger than some number, the slope of this should be equal to roughly 1-to-1. And it's a log-log curve. This is a logarithm of this value. This is the log of this value. So you could draw it in natural scale. It would still be 1-to-1. That wouldn't change. And that essentially defines this behavior. Perfect timing. Perhaps not for you, but for Penn State. They would like us to be just a minute off. Okay. That's it. So, to backtrack, forget everything you knew about multiphase flow. We're dealing only with stuff dissolved in the aqueous phase now. We need to use Darcy's law to say how quickly that moves downstream. And if we know that, and we know what the concentration that's carried in it is, we can say something about what the arrival time and what the distribution along the res aquifer would look like. And we can say something about that distribution in terms of the coefficients which control its behavior, in terms of advective transport and diffusive transport. And so next time we'll look at some simple 1D and 2D solutions for this equation, what they look like, and again bring it back to rationalizing this picture as well. Okay. Thank you very much. Any questions as you sprint for the door?